Okay, energy use and the environment. I'm not going to test you on this, but I think it's a very interesting topic that relates real life to chemistry, and so we're going to talk about it. So in the U.S., according to the data used in this book, each person uses over 100,000 kilowatt hours of energy per year. That's a lot of energy. Most of it comes from the combustion of fossil fuels. So fossil fuels are things like oil, natural gas, I think even coal counts as fossil fuel. And so these are combustible materials that originate from things that lived a long, long time ago. So we can look at the sorts of reactions that occur here. So carbon and oxygen combine to form carbon dioxide. Methane burns with oxygen to form carbon dioxide and water. Something like octane, which would be found in gasoline, burns, combines with oxygen to form carbon dioxide and water. And the heats of reaction for all of these are negative, because the point of burning a fossil fuel is to release energy, right? It's got energy stored into it. So one way to evaluate fuels is to look at, well, how much heat do you get compared to or relative to the amount of carbon dioxide that's released? Because whether or not global warming is real, carbon dioxide levels in the environment are definitely on the increase, and that can't be a good thing, so we should try to reduce that. So a better fuel is going to have a higher ratio of heat to carbon dioxide production. Oh, I thought I had a table showing that. So we could look at that right here. So both of these are creating 1 mole of carbon dioxide. So the heat of the heat of reaction here, this would give us minus 393 kilojoules. It would give us 393.5 kilojoules for 1 mole of carbon dioxide. This is going to give us 802 kilojoules. So burning methane instead of carbon from coal is going to give us more energy for the same amount of carbon dioxide that's put into the environment, into the atmosphere. So if we need the same amount of energy, that's going to result in less carbon dioxide emissions. So that's good. This looks like a really nice hefty number, 5,074 kilojoules. But if we divide that by 8, let's see what happens. Then we get, I have to write something here. It's going to be minus 634.3 kilojoules per mole of CO2 released. So better than coal, but not as good as natural gas. Any questions? We talk about, reducing your carbon footprint, right? So using natural gas instead of coal or gasoline is going to reduce your carbon footprint. It's going to produce less carbon. So fossil fuels cannot be replenished because, we don't have new things being fossilized. At the rate of consumption, they predict that oil and natural gas supplies will be depleted in 50 to 100 years. That's a cheerful thought, isn't it? Where does all of that get used? Well, here's a pie chart. Residential, commercial, industrial, and transportation. So, the development and manufacture of hybrid cars and electric vehicles is going to help put a dent in this, in the use of fossil fuels for transportation. Here's a graph of energy consumption by source. And we can see how this has changed over the past few decades. So petroleum use, it went way up here, and then it took a dive, and it went back up again. Some of these dips are caused by price changes, which sometimes is just political. Here's natural gas and coal. Now, petroleum products and coal are both decreasing fairly recently. Renewable energy would include solar power, wind power, because that's something that's not being consumed, right? And then nuclear electric power is in the purple. Any questions? Yeah.
Isn't there also the water turbine power too?
Water turbine power would be considered a renewable energy source.
Yeah, you were just listing off
Oh, yeah.
power and everything.
Yeah, I missed it. Those were the two that came to mind. Yeah. So, like, at Pine Flat Dam, you've got water coming down into the Kings River. Gravity is pulling the water down. We can use the water moving, which it would be doing anyway. We can use that to turn turbines and generate electricity. So when you burn a hydrocarbon, you produce carbon dioxide and water. And yeah, too much carbon dioxide is bad, but it's not like toxic or anything because there is carbon dioxide in the air anyway. And water's nice, right? Why does this cause pollution? Well, the gasoline in your car is not pure octane. It's not even pure hydrocarbons. It's got other stuff in it. So there are things that have been added, but most significantly are impurities in the fossil fuels. Could those be removed? Could we provide a pure gasoline? We could, but the energy required to do that would probably be more than what we'd get out in the end. It's not economically profitable. So we've got harmful materials get added to the atmosphere, and those are the things like nitrates and sulfur dioxide and things that cause acid rain. So the Clean Air Act, I forget when that happened, but that has actually had a positive impact on the cleanliness of our air. And so we can look at the percent change in these pollutant levels between 1980 and 2013. And we see that SO2, which forms sulfuric acid and contributes to acid rain, carbon monoxide, NO2, which also contributes to acid rain, and ozone. These have all gone down, so that's encouraging, making progress in the right direction. So carbon dioxide that guy's nuts. Carbon dioxide is a greenhouse gas. So what does that mean? What does a greenhouse do? So a greenhouse is like a house made out of glass, right? And so the sun comes through the glass and it warms things up inside, which is the same thing that happens outside the greenhouse. But because it's made out of glass, it traps the warm air inside. And so it could be freezing outside, it can be nice and warm inside the greenhouse without any added heat. There's no furnace or anything in there, it's just the sun. Carbon dioxide acts like a greenhouse for our planet, which is very necessary because planets without an atmosphere are extremely cold and would not support life. But balance is always the thing. So carbon dioxide allows light from the sun to reach the earth, but then it traps the heat, the infrared light, that is reflected off the Earth's surface. And so it traps heat, and so the amount of CO2 in the air is related to the average global temperature. So we can document that CO2 levels have been steadily increasing, and current observations suggest that the average global air temperature has risen 0.7 degrees Celsius in the past 100 years. And the models suggest that this could continue if we don't stop this increase in CO2.
Isn't it also suggested that it will have not an exponential effect where it will increase the difference?
Yeah, I have not actually studied this because there's other things that are more important to me. But yeah, there's a question of, well, if the CO2 doubles, does the temperature change double? Probably not. How is it related? And that's an excellent question. And all of this is based on models and observations, statistics, and statistics can be used to prove almost anything if you twist them enough. And so I'd like you, whenever you hear the results of these studies in the news, don't take that as absolute truth. Because no scientist will claim that what they've found is absolute truth, because you can't prove anything to be true. You can only prove things to be not true. It may be what is currently held to be true, but we should always be somewhat skeptical of findings like this. So here's our carbon dioxide from back in the 1800s up to current times. We see that the carbon dioxide concentration has increased significantly from about 290 parts per million to almost 400 parts per million. That's a significant increase. Now, what's that going to cause? Well, some models predict more severe storms, more floods and droughts, shifts in agricultural zones, rising sea levels, changes in habitats. I mean, it could be really, really terrible. Or it might not, right? These are models. We hope that the people who make them are, just observing what they see and not having some political agenda or anything. It's a suggestion of what might happen. Yeah?
That's just from the last 60 years, though, right? It's not, like, considering anything before that? Like, that's a 60-year gap right there. It's not considering...
No, this isn't a 60-year gap. This is from 1860.
Oh, I'm sorry.
Yeah.
Well, even then, I mean, the Earth is technically older than that.
Right.
So that's not...
Yeah. So we have limits in what we can look at, right? Because, before there were people living in North America, what were the CO2 levels? What was the average temperature? How do you figure that out? Well, there's ways that you can infer what that was. They can take rings from trees, and based on how wide the rings are, they can estimate the temperature. Is that going to be accurate to the nearest tenth of a degree Celsius? No. Is it going to give us an idea? Sure. But it's not like we had weather stations present and we've got data from the entire life of the Earth. I mean, we can't even agree on how old the Earth is, right? So all of that data is, subject to interpretation. How much weight do you put on that? How much error is in those measurements? It's a little hard to tell. And we do know that the average temperature goes up and down. Do you call an average over 1 year? Do you call it over 1 month? If you look at a monthly average, of course it changes. In the winter here, it's colder than it is in the summer. That's a natural variation. There are longer variations as well. And so this 0.7 degree increase in the last 100 years could be due to the increase in CO2. It could also be part of just a normal up and down trend that we don't have the evidence to see. So, anybody else have any questions? So this is interesting, and gives us a chance to do some practice here. What mass of CO2 in kilograms does the combustion of a 15-gallon tank of gasoline release into the atmosphere? So in order to do this, we have to make some assumptions. We're going to assume that the gasoline is pure octane. Is it? No. But this will be representative. So we're going to assume that it's C8H18 and that it has a density of 0.7 grams, per milliliter. So we want carbon dioxide and we've got octane. So we're going to need a chemical equation here. So C8H18. When something burns, it reacts with what? Oxygen. And it's going to form carbon dioxide and water. We have to balance the equation. So here we've got 8 carbons. So if I put an 8 in front of CO2, that gives me 8 carbons over here. Here I've got 18 hydrogens. And over here they're coming in pairs. So I need 9 moles of water. And then we're leaving oxygen. We've got 2 times 8, so we've got 16 oxygens here and 9 oxygens there. We add those up and that's 25. But oxygen comes in pairs. 12 and a half. Yeah, so we can do a fraction in here and say, well, that's 12 and a half or 25 halves of the oxygen. And then if you were requested to provide a balanced chemical equation, you'd have to multiply all of that by 2 to clear that fraction out. They don't ask us for a balanced chemical equation. We can use this one. This is balanced, it works. This tells us that we get 8 moles of CO2 for every 1 mole of octane. And that's what we need. We just need the relative thing there. So we can leave this alone. So what's our starting number? 15 gallons. So we've got 15 gallons of gasoline. And this is a rough calculation. So we're just saying 15, 2 sig figs. 15 gallons, and we're going to call that C8H18. And we want to get to mass of CO2 in kilograms. So we're starting with gallons of octane, and then we need to go to some unit of volume, and we're maybe like, I don't know, I don't want to start there. So we'll go back over here. We're getting to, kilograms of CO2. Well, we're probably going to end up with grams. Where do we often get grams from? Moles. So that's moles of CO2. We've got our chemical equations, so we have moles of octane. How can we get from gallons of octane to moles? We need the density, and we need to get grams in there. So I didn't leave enough space up here. Oh, I know what I'll do. We're going to use this. So we want grams of octane so that we can go to moles. We've got the density of the gas, so milliliters. So we need to get from gallons to milliliters. Hey Siri, how many milliliters are in 1 gallon?
1 gallon is 3,785.41 milliliters.
She's so helpful. Okay, so there we have that. We don't have to do all kinds of little steps in between because we had access to the conversion, so we can go from gallons to milliliters. The hard part of this problem is figuring out what we're going to do. Once we have a path, and I would really encourage you to write that down, then we just have to do it. It's all things that we've learned how to do. So we're going to take our 15 gallons and we're going to convert to milliliters. And Siri. Oh, come on, Siri. She went away. Hey Siri, how many milliliters are in 1 gallon?
1 gallon is 3,785.41 milliliters.
I like how she doesn't, give me a hard time because I just asked her that and can't I even remember for 5 minutes? No, I can't. So milliliters, gallons are canceling out. And then we were going where? We were going to grams. So here we're going to go to grams of octane and from milliliters. And that's the density that was given to us. So 0.70 grams per 1 milliliter. Milliliters cancel. And now we are into a more standard stoichiometry sort of situation, which would be grams to moles to grams, except we're going to kilograms at the end. So grams of octane to moles of octane. So we need the molar mass of octane. 8 times 12.01 plus 18 times 1.008. $114.224. Moles of CO2 to moles of octane. 8 moles of CO2 to 1 mole of octane. From the chemical equation. And we ran out of space, which happens sometimes. So I'll just go on to the next line. We need grams per mole. And that's carbon plus 2 oxygens, that's 44.01. And then we have to convert to kilograms. So grams on the bottom, kilograms on the top. Kilo means 10 to the 3, so 1 kilogram is 1 times 10 to the 3rd. So I've got 15 times 3,785.41 times 0.7 divided by 114.224 times 8 times 44.01 divided by 1,000. $90.14 kilograms. 90 kilograms of CO2. My car has a 15-gallon tank of gasoline. How many times did I fill that this week driving back and forth? 90 kilograms, that's a lot of CO2. Kilogram is about 2 pounds, so 180 pounds. The mass of a good-sized adult in carbon dioxide. Any questions? Renewable energy. So the greatest source of energy is the sun, right? And we've got technologies being developed to capture that energy. Parabolic troughs, solar power towers, dish engines, those can all concentrate the sun's light and make electricity. You can use the solar energy to decompose decompose water into hydrogen and oxygen, and then you can use the hydrogen as a fuel to power a vehicle, say, or a piece of equipment. And this reaction of hydrogen combining with the oxygen in the air reforms the water without any pollution. And that gives off a nice amount of heat without contributing carbon dioxide. Now the thing about like an electric vehicle, you're like, yeah, my vehicle's electric powered, it's not producing any CO2. Well, where's the electricity that you're using coming from? Right? Is it coming from solar panels? Well, then it's not producing any ongoing CO2. But how much CO2 was used in the fabrication of the solar panels? I mean, if you investigate this back far enough, you're like, nothing's good. Everything is bad. It's all relative. It's all relative. pictures. Okay, so I made a mistake on this slide. And what I did is when I typed this into my calculator, I had a 2 here. So I had 2,785 instead of 3. So the answer is not 90. Let me fix this real quick. Slow calculator. Using the correct number, it's 122.5. So 122.5 kilograms of CO2. So we call that 120 kilograms of CO2. So that is a correction to that problem.